resistance is nothing but the resistance which has been created because of the sheet of material of the semiconductor. We call it as a sheet resistance, because in almost in all the fabrication process, as we are discussing, the metal or whatever the semiconductor we are using, so all these semiconductors we will be used in the form of layering architecture only. So when you use the layering architecture, then obviously if the current is flowing in such a material, means then because of the friction or because of the movement of the charges, so there will be a resistance also for the movement of the charges. So what is the resistance which has been exerted for the current carrying semiconductor? So we need to understand. So for that we have studied a sheet resistance. Okay, so what is this sheet resistance? The sheet resistance is nothing but the resistance in a square meter. We are going to call it as a sheet resistance. So you can see in the diagram we had a resistance between RAB. So the resistance between RAB we are going to calculate from the formula, that is nothing but rho L divided by A, where A is nothing but a cross sectional area. So for this cross sectional area, so we know that the thickness of the wafer is T, and the width is, we have represented it as W. So therefore what I will do is, in the expression RAB is equal to rho L by TW. So what I will do is, I will replace the area with T into W. So if I do that, what you will be getting, RAB is nothing but rho L divided by T into W. So if you do that, what happens, your the resistance between the two ends of your sheet material, or the for the sheet semiconductor, so it will be, that is nothing but rho L divided by T into W ohms you will be getting. Okay, so and now you can see here, if the length and width whatever you have taken the sheet material, if it is same, so means what, in the square rectangular shape you have taken the sheet resistance, means then your RAB is nothing but rho L divided by A. So that sheet means, the square type of resistance we are going to call it as a sheet resistance. So the sheet resistance expression we can give, see here, that is nothing but rho L divided by, that is rho divided by T. So you can see from the expression itself, you can say that the resistance, that is the sheet resistance, does not depend upon the cross sectional area. So what it depends, it depends only on the, directly depends upon the resistivity of the material, and it is indirectly it depends upon the thickness of the material. So as the thickness of the material increases, the resistivity also, resistivity reduces. Whereas in the case of resistivity, if resistivity increases, means sheet resistance will increases. However, if the thickness is reduces, means then the resistivity will increases, because they are inversely proportional to each other. Okay, so this is how you are going to do the calculation in the case of sheet resistance. So there is no much difference between your sheet resistance and the resistance between the two end terminal. When the length and width of the material, if it is uniform, then such a material or such a shaped sheet resistance between them, we are going to call it as a sheet resistance. Okay, and typically we will be using this sheet resistance for different technologies. So in most of the cases, we will be using a 5 micrometer, that is a technology for the implementation of the VLSI fabrication process. So in the 5 micro technology, so what are the different sheet resistance we will be using for different elements of your MOS transistor fabrication process? It has been summarized over here. You can see for the metal it is 0.03, for the diffusion it is 10 to 50, and for the polysilicate that is 2 to 4 mm, and polysilicon it is 15 to 100, and for N channel it is 10 power 4, and for P transistor it is for 2.5 into 10 power 4. So we are going to make use of this sheet resistance. Okay, so from the use of this sheet resistance, we can able to calculate the whether the given transistor is a pull up transistor or a pull down transistor, also we can do it. Okay, and we will be using one more equation, that is nothing but R is nothing but, that is a channel resistance we will be using. So what do you mean by channel resistance is the resistance which has been exerted in the channel. You know, right, in a MOS transistor, either it may be a PMOS transistor or it may be a NMOS transistor, we will be using the channel, right? So for that channel, the resistance will be induced when the current flows across the channel. So what is the amount of resistance it has been included or it has been induced in the channel, we can able to create from the expression, that is nothing but R is equal to Z into RS, where R is nothing but a resistance of the channel, that is R is equal to Z into RS. So what do you mean by RS? So just now we have studied, right? So RS is nothing but the sheet resistance of the material, whereas Z we are going to call it as a impedance. We are going to call it as a impedance of the material. So the impedance of the material we are going to represent in the form of, it is a ratio of length to width. It is a ratio of length to width. We are going to call it as a impedance. That is nothing but Z is equal to L divided by W. So since if you consider a square sheet of resistance means, then both L and W will be equal only. So therefore we are going to represent this impedance in the ratio of 1:1. Okay, so we are going to make use of this impedance along with the sheet resistance in order to calculate the resistance of the your channel. Okay, so that is how you are going to calculate. Okay, so this is the table. What it gives is, so what are the different sheet resistance value we are going to tell it takes for the elements of the MOS transistor. So we are going to use all these elements in the fabrication of your NMOS transistor and a PMOS transistor. And we, as I told you in the last class itself, so there are different technologies are there for the fabrication process. So one of the technology what we are going to use is, that is a 5 milli micrometer technology, and one more is orbit, and one more is orbit 1.2 micrometer technology. Okay, so what is the difference between orbit and orbit 1.2 micrometer technology? We will see it later, but you can see what is the differences of resistance per square meter which has been used in all these technology for different element has been depicted in this diagram. Okay, I think we have means noted down this in the previous class itself. So we will go for the next one. Okay, so now the one more important parameter, that is one more basic important parameter what we are going to measure, that we are going to call it as an area capacitance. So why we need to study this area capacitance is nothing but because, so you see the fabrication process of your NMOS or it may be PMOS. See, first what we do is, let's say NMOS fabrication process. So in the NMOS fabrication process, if you remember what we have done, we have taken a P-type substrate. Okay, on the P-type substrate, first what we have deposited is, we have deposited a polysilicon. Okay, and after that polysilicon, what we have done, we go for the photolitho process. After photolitho process, what we have done is, we have etched some portion of the substrate so that I can deposit a N plus material for the source and N plus material for the drain. On top of this, what we have done is, again we have deposited a silicon dioxide, and after that we have deposited a dielectric, and after that on top of that for the gate terminal we have deposited a polysilicon. So means what, in each layering architecture, either we are going to use a silicon dioxide between the two layers to sandwich, or we are going to use a dielectric material. So especially for the gate material, you can see here we have a substrate, we have a dielectric, and we have a polysilicon. So therefore such a mechanism or such a configuration will establish as a capacitance between those two layers. Okay, so it is necessary for us to note down those capacitance. Okay, so in this slide, so we are measuring how we can know what is the effect of, or what is the amount of capacitance which will be generated over such a layering architecture will be given by using these equations. Okay, so we can calculate the area of capacitance between these two, that is a polysilicon and a between the polysilicon, dielectric, and a substrate. So there will be capacitance will be establishes. So how much amount of area that is undergoes for the capacitance we need to calculate. So for that we will be using the equation, that is nothing but C is equal to epsilon naught epsilon in A divided by D. Okay, so what you mean by A? A is nothing but a parallel plate capacitor, that is the area of the parallel plate capacitor, and D is nothing but the thickness of the silicon dioxide. So what is the thickness of silicon dioxide you have deposited on the top of the substrate? So this silicon dioxide, it will act like a dielectric also. And you know that E naught and E in ENS is nothing but it is the permittivity of the free space meter, free space. So we are going to calculate this in terms of Faradays per centimeter, and E that is epsilon ins is nothing but relative permittivity of the insulator. So whatever the silicon dioxide we will be using, no, so for that, so the relative permittivity will be there. So what is the amount of relative permittivity we need to calculate? So generally for SiO2 it will be 4.0, and for the permittivity, that is a free space permittivity, it is a constant value and it is standard. So for this constant value we are going to represent it nothing but epsilon naught is nothing but 8.854 into 10 power minus 14. These are the areas where we can expect a capacitance will be deposited or capacitance will be induced because of the deposition of silicon dioxide between the two metals or between the two semiconductor materials. Okay, so you can see here for gate to channel, see, you can see for the entire if you observe the table, for the gate to channel it is having the maximum value, that is a capacitance will be established for the area capacitance, whereas for the remaining cases it will be very minimum. Okay, but still we need to analyze, so how much is the area capacitance which has been introduced or it has been induced in the MOS transistor, so that this area capacitance, so how much of charge accumulation or how much of charge discharges will take place on this area capacitance, it is necessary for us to know in order to understand the complete behavior of the MOS transistor in three regions. So MOS transistor will generally work on three regions, so we know that what are those. So the first one is we call it as a saturation region, the second one we call it as a cutoff region, and the third one we call it as a linear region. So the amount of current which has been drawn from the MOS transistor or the amount of voltages which are applied, it may be source to drain, it may be source to gate. So it all depends upon the capacitance which has been introduced in these layers. Okay, so you can see the gate to channel capacitance is the more in the case of area capacitance which has been introduced or induced in the MOS transistor. Okay, so this is what the area capacitance layer, and we can able to calculate this area capacitance by using this formula. How we can able to calculate is nothing but it is a area, that is nothing but, so how much is the area for the given length and width divided by the standard gate area we are going to consider. The area capacitance of any gate or the area capacitance of the gate we are going to calculate, it is nothing but it is the ratio of, you can see here, it is the ratio of the area, that is nothing but L cross M, so L cross W, so whatever L and W is there, no, so that is the area divided by the standard area. So what is the standard gate area we have taken? That is nothing but 2 lambda into 2 lambda. Now for this diagram you can see here, so what and all it depends upon, you can see the length and width how much is there. So length is nothing but 20 lambda and width is nothing but 3 lambda. So therefore the relative area we have given it as 20 lambda into 3 lambda divided by the standard area. We know that, right? The standard area is nothing but the miniature size of the lambda based design rules. So we have taken it as 2 lambda cross 2 lambda. So if you do that means, so the lambda lambda will get cancelled and this 210 and this will be divided, so you'll be getting a 15. So that is nothing but the relative area capacitance of the gate terminal. The relative area capacitance of the gate terminal will be given as 15. Okay, and along with this we need to measure some more important parameters when you measure the area capacitance. So what are those area capacitances? So that is nothing but we will be measuring this area capacitance, that is the unit of area capacitance we will be representing in terms of Cg, and we are going to measure the capacitance, that is nothing but the unit of capacitance we are going to define as, it is the ratio of gate channel capacitance of a MOS transistor having length and width is equal to same. Okay, so means what? The unit area of capacitance or the unit area capacitance Cg is defined as it is the ratio of gate to channel capacitance of the MOS transistor having length and width which is equal to 2 lambda. Means for the standard gate area what we will be considering 2 lambda into 2 lambda, no. So for the standard area length, if it is 2 lambda into 2 lambda means, then that we are going to call it as a unit of capacitance. Okay, so when you want to calculate the unit of capacitance, so we have calculated, so for 5 micrometer process, for the 5 micrometer process, the capacitance value will be 4 into 10 power minus 4 Faraday picometer per micrometer square. So means what? Once again I am telling you, the capacitance value for 5 micrometer process, it will be 4 into 10 power minus 4 picofarad. Okay, so similarly for the 2 micro process, so it will be, the capacitance value will be 8 into 10 power minus 4 picofarad. And for the 1.2 micrometer process, so the capacitance value will be 16 into 10 power 14. Okay, so when you want to calculate the means the capacitance, that is the area capacitance, so it depends upon the several factors. So what it depends upon the several factor is, so first one is the area of the material. So how much is the area of the material you are going to consider for the gate diffusion, and for the n plus diffusion it will depends upon. And the capacitance the substrate, it is mainly depends upon, it also mainly depends in calculating of the area capacitance value. And the area of the polysilicon and the area of the n plus diffusion we will be means will be depending upon. See, all this dependency we can see it in the expression for this relative area itself. Okay, so it is taken account the area of the metals, and it is taken account the capacitance of the substrate. Along with that, it has taken account the account of the area, that is length and width of the polysilicon, and also the length and width of the n diffusion material it has taken. So this is how you are going to calculate the relative area of the capacitance in case of any capacitance which has been introduced in the MOS transistor. Okay, so I request all the students, you please make a note of this. Hmm. Shall we go for the next one?
Yes, sir.
Okay. So you can see the capacitance calculation for the multi-layer. So how we can use the capacitance calculation for the multi-layer, it has been given here. So the relative area of the metal. So how we are going to calculate is nothing but, that is the area, that is L into W divided by the standard area. So you can see the area, what, how much is the total area? The total area is nothing but 100 lambda. And what is the width? Width is nothing but 3 lambda. So therefore the relative area of the metal we are going to consider is 100 into 3 lambda, that is 100 lambda into 3 lambda divided by the standard size. So what is the standard size? 2 lambda into 2 lambda. So please do this calculation. What you will be getting, you please tell me. 100 lambda into 3 lambda divided by 2 lambda into 2 lambda. So how much you will be getting? Please tell me. That is the relative area. So you please tell me what is the lambda, how much relative area you will be getting. 100 lambda into 3 lambda divided by 2 lambda into 2 lambda. Tell me. Yes, anyone?
75 lambdas.
Yes, 75 you will be getting. So that is the relative area. And based upon the table what I have given you, so the metal 1 capacitance, so the metal 1 capacitance for 5 micrometer it is 0.75, 0.075. So if I multiply 0.075 into 75, so you will be getting 5.625 unit capacitance for the metal 1. Similarly, for the polysilicon area, you will be getting that is 4 lambda into 4 lambda, that is a polysilicon area what we have shown in the diagram. So if I multiply, that is 4 lambda into 4 lambda, plus 3 lambda into 2 lambda. If I multiply means, then you'll be getting 22 lambda square. That is a polysilicon area you'll be getting, and the polysilicon you'll be area. So that is a polysilicon area. So we can calculate the polysilicon capacitance by using nothing but the polysilicon area divided by the capacitance for the polysilicon. So the capacitance for the polysilicon in the previous diagram, it was 4. Okay, so you can see the capacitance of the polysilicon, it was zero point 0.4. So if I do the calculation for that, so you'll be getting 22 divided by zero point 0.4, so you'll be getting 0.55 unit capacitance. Okay, so similarly the capacitance of the gate is nothing but 1 unit capacitance. So therefore the total capacitance is nothing but the capacitance of the metal, the capacitance of the polysilicon plus capacitance of the gate. So if you totally combine all this, you will be getting 7.25 unit capacitance for this diagram. Okay, so this is how you are supposed to do the calculation for this area capacitance. The next one is delay unit. Okay, so this is delay is also plays an important role when you want to do the calculation, or when you want to measure the performance of the MOS transistor. So why basically this delay unit it will be used is that, because since the MOS transistor you'll be having so many coupling of the one circuit to another coupling will be there. So when the signal wants to propagate from one circuit to another circuit, so the amount of delay or the amount of time taken for the signal to propagate from one instant to another instant, or from one circuit entity to another circuit entity, plays an important role if we are going for if you're going for a flip-flop based circuits. So in flip-flop based circuit, what happens is we will be using the timer or a counter in order to accommodate the events. So if it takes more amount of time than the clock frequency means, then whatever the synchronization which was needed for the asynchronous mode of transmitters or asynchronous mode of resistors, so there it will be affected for this delay unit. So therefore when we want to analysis the MOS transistor, so we should give a prior intimation, or we should give a proper priority for this delay unit calculation. Okay, so in VLSI technology there are different types of delay will be encountered in the MOS transistor. So one of the delay unit what we will be using is, or the delay time we will be calling it as a propagation delay time. Okay, and one more we will be getting a contamination delay time, and some more delays we will be getting in the case of rising edge, or in the case of when we generating the square waves, or when we generating the triangular waves, or when we generating the signals which is associated for the timer or the counter. So then we will get some more type of delays, that is nothing but rise time, fall time, and edge time. So you need to make sure that all these delay units has to be calculated properly, so that there will not be any mismatch, or there will not be any unsynchronization in the MOS transistor will takes place. Okay, so therefore, so we will be using these fundamental, that is a fundamental delay elements, in order to understand how this delay unit will be derived. And one more thing what you need to understand is, so this delay unit we will be using, or we will be calculating through the use of tau parameter, and this tau parameter it depends upon which type of technology we will be using. Okay, so this tau parameter for 5 mm technology, so the tau parameter will be zero point 0.1 nanosecond for the delay. Okay, and for the 0.2 mm technology, the tau value has to be 0.064 nanosecond, and for the 1.2 orbital technology, that is orbit technology, so this tau value has to be a 0.046 nanosecond. Okay, so these are the delay units. It has been specified in the data sheet of the MOS transistors. So when you create or when you fabricate any MOS transistor, so you need to make sure that your delay units should not cross these values. So once again I am telling you, for 5 micrometer technology, the tau value has to be 0.1 nanosecond, and for 2 micrometer, that is orbit technology, the tau value will be 0.064, and for 1.2 orbit technology it is 0.046 nanosecond has to be the delay unit. So if you have these delay units means then your synchronization with the rest of the unit or rest of the circuit entity will be more. Okay. And after studying this delay unit, the one more important delay what we are going to encounter is that is nothing but the propagation delay in the case of inverters. Okay, so basically inverters we are going to use in the stabilization of your signals, and we want to get a complement of the given signal means then we will be using the inverters. So when you use the inverters, so basically what inverter it is nothing but switching from positive to negative and negative to positive. So when you want to do the switching from positive to negative or negative to positive, the rise time and fall time has to be minimum, means the roll off rate has to be infinity ideally. But in the inverter delay cases, you will not get a 100% roll off rate, that is 90%, 100% you will be not getting, because there will be some slope will be established. So because of that slope establishment, the propagation delay will be encountered in the MOS transistor. So this propagation delay, what we are going to call it as, it is an inverter which is the difference in time, that is nothing but the difference in time when the output switches from either from 0 to 1 or 1 to 1 to 0. So the time taken for the means the time taken for the signal to reach from 0 to 1 or 1 to 0, we are going to call it as a propagation delay in the case of inverter delay concepts. Okay, so this is how the propagation delay will takes place in the case of MOS transistors. It has been depicted over here is, so you can see for the first time, so the propagation delay it was included, that is 1 tau it has been generated, whereas in the second tau it was being generated as 4 tau. So the maximum propagation delay which has been incorporated in this given signal, that is a NMOS inverter pair delay, it is 1 tau plus 4 tau, so it will be total 5 tau has been incorporated in the inverter's delay. Okay, so this is how you are going to calculate, means you are going to calculate the delay which has been incorporated by all the elements in the given circuits. So if you sum all the delays which has been encountered in the MOS transistor means, then you will be getting the total propagation delay which has been experienced by the signal during the propagation over the MOS transistors. Okay, so that has to be you need to understand. Okay, and one more important means inverter delay what we will be using is in the case of when I use the CMOS inverters with minimum size. Okay, so we call it as a minimum size. So what you mean by minimum size is when we use 2 lambda into 2 lambda transistor. So that concept or that mechanism we are going to call it as a minimum size CMOS inverter. So the amount of delay which has been incorporated by the minimum size CMOS inverter, it has been given in this diagram. So you can see here we have taken one inverter and followed by one more inverters. So since the inverter combined, we need to provide it with a blocking capacitance. So therefore we have given a blocking capacitance, two blocking capacitance we have given. So one each blocking capacitance will be having a 2 unit capacitance value. So you can see here for the first capacitance, the amount of propagation time or the propagation delay which has been incorporated is 2 lambda. Whereas in the case of second one, it is 5 lambda. So if I sum this 2 lambda plus 5 tau means, then you will be getting a 7 tau as a total propagation delay which has been incorporated or which has been induced in the case of standard sized inverter delays. Okay, so this is how you are going to estimate the delay inverters in the MOS transistors. Okay, so the next one is how we are going to encounter for the rise time estimation and the fall time estimation. Okay, so it is necessary for us to describe the delay estimations of the CMOS inverters by charging and discharging the capacitive load. So the CL is nothing but the capacitive load you can see in the diagram. So it is necessary for us to know the charging and discharging capacitive load. So the first one, what we are going to call it as a rise time estimation. So we need to note down. So what is the amount of time, that is the V out it has taken to rise from 0 to 1. We are going to call it as a rise time. So from the diagram you can see here the rise time is nothing but the time taken. So here you can see the slope, the time taken for the signal to reach from 0 to 1, we are going to call it as a rise time model. So this is the circuit what we are going to use in order to calculate the rise time value of the CMOS inverter delay. Okay, so I request all the students to please kindly note down this diagram. Please make a note of this diagram. Is it over?
Yes, sir.
Okay. See, the rise time we were going to calculate with the use of, that is TR is nothing but VDD into CL divided by beta into VDD minus VTP whole square. We are going to use the equation in order to calculate the rise time value. Similarly, we are going to use one more important model, that is nothing but a fault time model. So we are going to estimate the amount of time taken. We are going to estimate the amount of time taken by the signal to reach from 1 to 0 by using the expression that is nothing but tau f. So the tau f, just wait a minute. Am I audible?
Yes, sir.
Yes, sir.
Okay. So with this fault time estimation, so the fault time we are going to represent in terms of TF, that is a tau f, whereas the rise time we are going to estimate or we are going to represent in terms of TR. So from the use of this fault time and rise time, we can able to see how much is the propagation delay which has been incorporated in the MOS transistor. We can able to calculate. Okay. The next one is driving large capacitive load. Okay, so it is necessary for us to understand, or it is necessary for us to know. So what is a capacitive load which can be drawn from each subsystem in the entire IC manufacturing process? We need to understand. So when signals are propagated from on chip to off chip, there will be problem will be associated, and those problems we are going to call it as a driving large capacity load problems. Okay, and typically, so when I say typically, so for example, for the off chip capacitance, so generally the off chip capacitance should be high when compared to the on chip capacitance. So we have just now measured, the area capacitance. So when the system, or when the chip, entire circuit of the chip, if it is off, then the capacitive chip of the entire system, it should be generally high when you compare to the capacitance of the on chip cases. So this is, we are going to call it as a load capacitance. Okay, and this capacitance should pass through the low resistance value, otherwise longer delay will be occur in the entire IC circuit. Okay, so when you design or when you frame any VLSI connect integration, when you do it, so you should make sure that what is the driving capacity of each unit, whether it is possible for the signal to propagate or whether it is possible for the signal to pass through that subsystem, we need to understand. So in understanding those, so we will be using the driving large capacitive load. So you can see here in the given the diagram. So this diagram we are going to call it as a cascaded inverters as a drivers. So we are going to use the cascaded inverters as a drivers. So in this, so what we will do is we will make the circuit to have a pull up and pull down trans resistors. So just now we have understand the sheet resistance, no? So if the L and width ratio, if L is greater than width means then we are going to call it as a pull up transistor, that is a resistor. If L is small and width is large means then we are going to call it as a pull down resistor. Okay, so by using this channel length and channel width, we can able to minimize the resistance in the driving capacity of the load. So by minimizing the resistance, we can able to achieve maximum amount of current which can be flows over the entire IC circuit, so that all the devices or all the circuit entities will be run with the proper power rating values. Okay, so these are the one of the simple circuit diagram what we will be using in order to know the driving capacity of the loads in the case of larger IC connected circuits. Okay, and the last concepts what we are going to see is nothing but super buffer. So generally what happens is in the previous case, whatever we have considered, that is nothing but pull up transistor or a pull down transistor. So they are not capable in driving the same load for the capacitance values. So means what, sometimes pull up transistors will be more, whereas sometimes pull down transistors will be more. So means what, there is no symmetry between the pull up transistor and a pull down transistor. So in order to avoid this symmetry, so we go for one more type of buffering concept, and those buffers we are going to call it as a super buffer. So basically these super buffers are nothing but a symmetric inverting or non-symmetric inverting buffers which have a capability to drive a large capacitive load. Okay, super buffer are nothing but the symmetric or asymmetric non-inverting driver only, but they have a capacity of driving larger capacitive load. So you can see here in the diagram, so what basically this diagram you can be able to see here. So what is this? It is nothing but inverter only. So you can see we have a depletion transistor followed by one more transistor is there, and you can see one more depletion transistor, on below of that there is a MOSFET transistor is. So what we have done is we have connected one transistor and one more transistor. So but the difference what with the normal transistor or the normal inverter with the super inverter is here. So you can see the gate terminal of one transistor, that is a depletion transistor, is being connected to depletion transistor, whereas the MOS transistor gate terminal has been connected from one MOS transistor to another MOS transistor. So with this circuit configuration, we can avoid the asymmetry which has been incorporated or it has been established because of the pull-up sheet resistance or